changed since I was thinking about it because it thought the time changed. Like it said 9 o'clock, but it was thinking 7 o'clock. So the 7:30 alarm. So the 7:30 alarm woke me up at 8:30 because the time changed. So it didn't recognize that the time changed. Like it showed me the time. Yeah. Like it took the time out, but the alarm didn't recognize. The alarm actually.
Okay. Let's go ahead and get started again. I realize the clock says we're an hour early, but might as well take advantage of being an hour early too, right? I will try not to go for 2 hours. Although I could. So, some of you may not be aware, Jimmy Gaines had a court date last week. He is not going to jail. He has a deal where he goes to counseling, which he's already started apparently. He writes a letter of apology, which he's already done. And he gets to do 8 hours of community service. Now we can, discuss sentencing and all that stuff. And you can, come up with your own opinions on whether that's too much or too little, or if it's the Goldilocks approach to the situation there. But that situation has now apparently been resolved. He's got one more court date in 90 days to make sure that he's following up on all of this stuff. And presumably that will go well, and he will go on with his life, and so will we. So, we are reminded that every now and then in life we do something that we would rather not do. How many of you have thought at the end of the day, there is some period of time during that day that I would rather just have skipped over and not have had it? Maybe it's the hour during which you took a test. Maybe it's the hour that you overslept. Maybe it's the hour you spent at Vespers with somebody who really wasn't worth an hour of your time. Wouldn't it be good if you could just there at the end of the day just go back and delete that hour from your day? Yesterday we deleted an hour from the day, right? It's just, unfortunately, we deleted that hour when most of us were probably sleeping. I say most of us because I know how things go in a particular age, late Saturday night, or Sunday morning. So yesterday we had a 23-hour day. We just took an hour, we just chopped it out of there. And it's gone, never returned. Maybe, as we are sitting here with our new daylight savings existence here, and talking about the hour of sleep that we missed, although to be honest, most of you probably didn't actually miss that hour of sleep, you just slept the same amount of time and chopped an hour out of your wake time. Maybe we should take this daylight savings thing as an opportunity to remember what grace does for us. Because if you think about it, what God is doing for us through grace is basically He is deciding that He's going to treat us as though we just chopped all of those unfortunate moments out of our lives. For some of us, maybe we had a bad hour one day. For some of us, maybe we had a bad 24 hours. Doesn't matter how long or how short the period of evil is in our lives through grace, God has chosen to treat us as though that period of our lives no longer existed. You can imagine what it would do to all of our chronologies if we actually treated our lifespans in terms of how old we might actually be if we chopped out all of the bad stuff and just based our ages on how much good stuff we did. That'd be kind of an interesting experiment for God to pull. And then you could have the relatively older looking people who would have been good for longer, and then you could look at the people who were fairly infant looking, and you'd know that they had more time to lead it for who knows what reason. God gives all of us the chance through grace to essentially erase that stuff that we did that was sinful and selfish and counterproductive to godly living. And as we look at how God has essentially erased those moments from our lives, it reminds us of the challenge that all of us have in terms of how do we extend grace to other people. How do we learn how to treat other people the same way that God treats us, and to overlook those periods when they have harmed us? How do we learn to not only tolerate what our enemies do to us, but to actually love our enemies despite what they have done to us? This is the challenge that we have. Once we see that God has been gracious to us, then we have to figure out how we're going to be gracious to everybody else and pay it forward. Let's pray. Heavenly Father, we thank you for being here with us today. We thank you for having been with us over the past week apart. We ask that you would help us to better appreciate your grace in our lives. Help us as we appreciate grace and as we experience grace to be able to share grace so that other people will have a better understanding of you as well. We ask this in Jesus' name. All right, so midterm grades are out. Probably a number of you I didn't have to tell that to because you already looked. And most of you probably have an idea based on the midterm grades that the last test went reasonably well. And it did. I was actually pretty pleased with on average how things went there. I think the average was somewhere up in the mid-80s on that, which I thought was pretty good. And that average got skewed a little bit by some of the people down at the lower end of the scale there. There were roughly half of you that were somewhere in the A to A minus range. So this whole terrifying acid-base thing seems to have turned out pretty well for the most part. Let's hope we don't forget all of this acid-base stuff, because those people who are taking more chemistry classes are really going to need that stuff. So make sure you've got that stuff locked in the long-term memory there. Those tests will be back in your boxes later this afternoon, and I will have the updated grading printout posted this afternoon so you can see what those midterm grades are actually based on in terms of tests and quizzes and homework and labs. So you will have some idea of why your midterm grade is what it is. You can move forward from there and either maintain or improve as necessary. As I had talked to a number of you earlier this semester, I had mentioned that pretty much it was the stuff before spring break that was the harder stuff, and the stuff after spring break that was relatively less stressful. That means that you now are faced with the challenge of not letting up on things. This is the part of the semester where people tend to get maybe just a little bit overconfident and don't put quite as much of the time and effort into things as they did when you were struggling with buffers and titrations. if you put that same amount of time and effort and understanding going forward as you have put in the first half of the semester, the rest of the semester should turn out pretty well. If you start to slack off a little bit here because conceptually things aren't quite as trying for you, things may jump up and bite you at some point here. So be comfortable and confident in what you have achieved so far, but let's try not to get overconfident in this stuff here because we've still got plenty of opportunities for grades to move in better directions or in worse directions here. Your next quiz is coming up a week from today. We're finishing up this chapter that we started when we caught up in recitation before break. I mentioned that the homework that is assigned as being due for today can be turned in up until tomorrow morning. So I see a few of you were already ambitious enough to finish that off. So bring it by my office this afternoon or tomorrow morning. We've got until 11 o'clock to deal with that. We're going to go back to chapter 15 on Wednesday and Friday. That's another relatively short chapter, so we'll take 2 days on that one. So your quiz that is coming up a week from today will cover both of those relatively short chapters. And then we'll do one more chapter before we do test number 3 here. And a little jumping around to make things fit the way that I want them to fit here. So that quiz next Monday will cover chapter 19 that we're finishing here today, and we'll cover chapter 15 that we are working on Wednesday and Friday. So plan ahead for that. All right, so we left off last week, not last week, the week before, on Thursday. We had talked about complexes and looking at these being combinations of ligands acting as Lewis bases and metal ions acting as Lewis acids and coming together to give us these complexes whose overall charge is based on the individual charges of the metal and the ligands. We talked a little bit about how we name these things and how Italian the chemistry starts to sound when we have all of the oros and the tris and the dis and all of this fun stuff here. You write nice big long names. It's kind of super califragilisticexpialidocious, I guess. So we talked about that. We looked a little bit at things that are al dente to do this chelating thing. We looked a little bit at coordination numbers and geometries, and if the coordination number is 2, something is linear. If the coordination number is 4, then it's either tetrahedral or square planar, depending on circumstances. We saw that if you have something that's square planar, you might have different isomers depending on the relative positions of the ligands, and then we have our whole cis-trans thing that comes into play. And we saw that as we go into a coordination number of 6 with an octahedral geometry, that you can still have potentially cis and trans isomers. We also saw that if you have 3 ligands of the same kind, you also have some potential for isomers there. We use some slightly different labeling in terms of the FAC isomer and the MER isomer. And those terms, FAC and MER, are not given there in your textbook. So that's bonus information that I'm expecting you to know above beyond the textbook stuff there. All right, so we're going to finish off by looking at electrons within these transition metal complexes here. So let's start by looking at the electron configuration for manganese. Yeah, electron configuration. We haven't thought about those in a while, have we? And you remember that when we did these, they were relatively easy and not terribly stressful, right? so let's go over a review of electron configurations. So we're going to do the complete electron configuration for manganese here. So where do we start? 1s2, 2s2, 2p6, 3s2. Now keep going, so we're doing manganese and not manganese. Right? What comes after the 3s2 here? 3p6, 4s2, 3p5. Right? Manganese should have 25 electrons based on its atomic number of 25. Remember, we just put those electrons in the right levels and sublevels and orbitals from lowest energy to highest energy, and the periodic table helps us count things up very nicely there. Somebody was very generous to us when they organized all the elements that way. That familiar? Got one more thing to put on your review list here. I told you we were going over almost everything from last semester at some point here. Okay, so there is the electron configuration for the manganese atom, and remember we can abbreviate these, and we can write this as argon 4s2 3d5. Remember, we got those nice abbreviated configurations based on the noble gases there. So, how do things change when we look at the electron configuration of the manganese 2 ion? What's the difference between the manganese atom and the manganese ion? We have 2 less electrons, right? Positive ions have fewer electrons, negative ions have more electrons. Okay, so if I want to write the nice, full, complete electron configuration for the manganese 2 ion, how do I write that? 1s2, 2s2, 6, 3s2, 6, 3d5. So if you were thinking, wait a minute, why are we taking them out from the middle here? Remember what happens with our transition metals. Remember, you take out the s electrons first, and then you can start taking out the d electrons there. So remember, those transition metal ions are slightly quirky based on our normal expectations of what ought to happen there, right? So remember, all transition metal ions, you always take out those s electrons before you take out the d electrons. So we went up to manganese 3, then we start taking away from the 3d sublevel there. Okay? Is that a useful review of electron configurations? That seemed vaguely familiar from probably, 3-4 months ago, somewhere in there. And now that you've reviewed these, you want the next test to have lots and lots of electron configurations again? You'll see. All right, now let's look at these electrons in the d sublevel here. How many d orbitals are in a d sublevel? There are 5 d orbitals in the d sublevel. Remember, you have 1 s orbital in the s sublevel. You have 3 p orbitals in the p sublevel. Remember, that makes sense because each orbital wants to have 2 electrons, so that explains our total capacity for electrons there. Okay, so in this manganese 2 ion, we have 5 electrons in the d sublevel, and these 5 electrons are somewhere in these 5 orbitals, right? So here's our 3d sublevel. And if we're going to put 5 electrons into this 3d sublevel, into these d orbitals, how do we put these electrons into the d sublevel? 1 per orbital, right? Remember, electrons don't really like each other all that much because they all have these negative charges and try to avoid each other. So if if I have 5 electrons and 5 orbitals available, each of those electrons is going to want to have their own room to live in. And what do we know about the spins of these 5 electrons? They all want to have the same spin, right? They all want to have their own space, but they all exert peer pressure on each other and all want to be the same in terms of how they behave. Just like the donut, right? Okay, so if I have a manganese ion, a manganese 2 ion with those 5 electrons in the 3D sublevel, all 5 of those electrons occupy different orbitals, and they all have the same parallel spin. This manganese 2 ion, we would say, has 5 unpaired electrons. Unpaired because they are all in separate orbitals. So I brought with me some models of what these d orbitals look like. Pull these up here. I can look like somebody who's named John Travolta should be butchering it. And this is what they look like. You got the one that's kind of an oddball, with the rest of them kind of like really excited looking p orbitals here, right? Okay, so let's talk about these ions now in the context of these complexes that are formed. In this manganese ion, if it's just a manganese ion out there all by itself, nothing else is around, all 5 of these orbitals are equivalent in energy. If that manganese ion is interacting with ligands, those orbitals no longer will all necessarily have the same energy. The question is, why do different orbitals now have different energies? Well, the reason that these orbitals are going to have different energies, if we want to think about this in a relatively simple way, and I suspect that you do, is that if I have an electron in an orbital that's pointing toward where a ligand is that a low energy situation or a high energy situation? Well, electrons don't like each other, right? So if I'm trying to put the metals electron in the same general area that the ligand electrons are, that's a high energy situation. So orbitals that are pointing in the directions where the ligands are and are going to be putting the metals electrons in the same places where those ligand is trying to put its electrons are going to be relatively high energy orbitals. If a metal's orbitals are putting those electrons in places where the electrons are not, then those are going to be relatively low energy orbitals. Okay, so with that general principle, let's look at what we might expect to happen to these different d orbitals if we are making an octahedral complex ion. So if I have an octahedral complex ion, I'm going to have ligands coming in from all of these different directions, right? I'm going to have one coming in here, I'm going to have one coming in here, I'm going to have one coming in here, one coming in here, and then top and bottom, right? You can see how your octahedral geometry fits very nicely on this orbital model that I have here. So if I look at this particular d orbital with its somewhat unusual shape here, is this orbital pointing toward where the electrons are coming in at? I got ligands that are coming in top and bottom here, where this orbital happens to be. So if I have an electron in this orbital, that electron is going to start interfering with these electrons that are coming in from the ligand. That's a high energy situation, right? So I would expect this particular orbital to be relatively high in energy, because if I put an electron in this orbital, it's going to start bumping into ligand electrons, and that's a high energy situation. So let's put this one nice and far away from me here, because this is a high energy orbital. And what about this orbital here? Well, now if you look at this orbital has, the electrons are going to be kind of in between where those electrons are coming in at, right? And And so this is going to be a relatively low energy d orbital because the ligands can kind of sneak in between where this orbital is and where its electrons are. So let's put this nice low energy one close to you here. And what about this one? Go ahead. Okay, so if I have an octahedral geometry, I've got 6 pairs of electrons coming in from ligands, right? And just to make it easy, we'll say that they're coming in left and right, front and back, top and bottom. And so when I bring in a ligand, it's going to be bringing electrons along these poles here, right? Okay. This orbital is where the metal wants to hold its electrons. And in this particular orbital, I see that this particular orbital is going to hold 1 or 2 electrons somewhere along this axis here, right? Which is the same direction in which 2 of our ligands would like to come in from. And so if I have an electron in this orbital, that electron is going to be bumping into electrons coming in from my ligands. And that's a high energy situation because electrons don't like each other. Where that's in this one, then these electrons are being brought in from the ligands. They're coming in between the area on the metal where the electrons are.
So the metal is in the middle.
So the metal is right in the middle. So there's our metal nucleus right in the middle of the old orbital there. All right, so based on what we've been talking about, is this d orbital relatively high energy or relatively low energy? That's relatively low, right? Again, where the metal has its electron or electrons in this orbital is in between where the ligands are. So we got that one there. What about this one? Is this a high energy or a low energy? That's a high energy one, right? Because I got 4 ligands that want to come in to where this metal has electrons. So let's put that one up there. And what about this one here? That's another low energy one, right? And so if you look at the overall situation here in terms of these potential interactions between the electrons that might be in the orbitals on the metal and the electrons that may be coming in from the ligands, in this octahedral geometry, I have 3 orbitals that are relatively low energy and 2 orbitals that are relatively high energy. So my 5 d orbitals that I started with, that if this ion is all by itself are equal in energy, are now split into a couple of different sets. Same 5 orbitals, but different relative energies because they are now in a different environment. Okay, so now the question that we need to ask ourselves is, if I have this same manganese 2 ion, and I want to put 5 electrons into these 5 orbitals, how am I going to do that? Well, where will I put the first electron? In one of these orbitals that's low in energy here, right? So there's electron number 1. Where do I put electron number 2? In a different orbital of equal energy, right? And where do I put the third electron? In the other nice low energy orbital is equal in energy. So I've got these 3 electrons that I put in here that are in their nice low energy positions that are separate from each other. Now when I get to electron number 4, I have a choice, right? There are 2 things that I could potentially do. The first thing that I could do is to give this 4th electron a room of its own. Or what's my other choice? To pair it up in a lower energy spot here. Now pluses and minuses of doing both of those things, right? What's the advantage of putting electron number 4 up here? The advantage is it's not in the same orbital as any of the other ones, right? And the electrons prefer to be separate if they can. What's the disadvantage of putting it up here? It's a higher energy orbital. Okay, so it takes more energy to get an electron in here than it would to put it down here. So there are two different things that I've got to look at here. I've got this difference in the energy between the orbitals, but I also have the fact that it costs a certain amount of energy to put two electrons into the same orbital. And as it turns out, in different situations, these electrons may choose to do different things. What I have here is an energy difference that goes by a number of different names here. We'll call it delta O for an octahedral difference here. And the terminology that this particular textbook chooses to use is what's called the crystal field splitting energy. So when you see this reference to the crystal field splitting energy or this delta O, this refers to the difference between the energies of these d orbitals when that transition metal ion is in some kind of an octahedral complex. So basically what I am comparing is what I would call this crystal field splitting energy to my other factor, which I'm going to go ahead and call the pairing energy. When I talk about the pairing energy, what I'm talking about is the amount of energy that I'm going to have to expend if I want to put these two electrons into the same orbital with each other. Because if I'm putting two electrons in the same place, there's a certain penalty that ought to play for putting these two negative things in the same general vicinity. So the question that I have as I'm putting these next electrons in here is basically, what is bigger? Is my crystal field splitting energy bigger, or is my pairing energy bigger? And as it turns out, in different situations, I end up answering that question in different ways. I may have a relatively small value of that splitting energy there, where there's not a very large difference between the energies of these d orbitals. In this case, my small crystal field splitting energy is less than the pairing energy. And if that crystal field splitting energy is small, then it's going to cost me less energy if I just keep putting those electrons in orbitals all by themselves. So if I have a small splitting energy, then I will put those 5 electrons in 5 different orbitals. I will put electrons 4 and 5 into these higher energy orbitals because it costs me less energy to do this than it would cost me to try and make these electrons play nice with each other in the same orbitals. So that's one possible situation where my splitting energy is relatively small. In different cases, I might have a large crystal field splitting energy, so that my crystal field splitting energy is greater than the amount of energy that it would take to pair those things up. And if I have a large difference in this crystal field splitting energy, then what happens when I put the 4th and 5th electrons in here? If the difference is large enough, then it costs me less energy to go ahead and just put these in the lower energy orbitals with each other. And so I fill up my orbitals like that. So I have 2 different situations here which, if I do the right experiments, I can distinguish from each other. I can determine that the complex either has all of its electrons that are in orbitals by themselves and are unpaired, or I can have a situation where most of those electrons end up being paired up and I just have one unpaired electron. those will have different properties there. All right, any questions at this point? Now, we have some terminology that we use to apply to these different situations here. In this situation here, where the splitting energy between the d orbitals is relatively small, this is what we refer to as a weak field situation. Basically, when we say that we have something that is weak field, what we are saying is that there is a small splitting energy between those d orbitals. So when you see the terminology weak field, that means your splitting energy is small. When the splitting energy is large, as we have in this case here, this is what is commonly referred to as a strong field situation. Strong field basically means that the interactions between the ligands in the metal are more significant so that you have a greater difference in the energies of those d orbitals for the metal ion. So we have weak field in which the orbitals don't differ a whole lot in energy. We have strong field where you have a more significant energy difference between those d orbitals. As a consequence of having either a weak field or a strong field situation, we have different numbers of unpaired electrons in each of these cases. In the weak field situation, we have a maximum number of unpaired electrons. Because in the weak field situation, we can put electrons in separate orbitals as much as we possibly can. Where we have this maximum number of unpaired electrons, this is something that we refer to as being high spin. When we say high spin, what we are just saying here is that in this high spin situation, we have the maximum number of unpaired electrons. High spin means lots of unpaired electrons, basically. In contrast to the high spin situation that we see if we have a weak field case, in the strong field situation, we will have a minimal number of unpaired electrons. And when we have a minimal number of unpaired electrons, we will have what we call a low spin situation. So there's always going to be this correlation. When you have a weak field, you will have high spin. When you have strong field, you will have low spin. When you have weak field, it's easy to keep all the electrons separated from each other. When you have strong field, it's easier to get all those electrons paired up with each other. And so we have strong field versus weak field and high spin versus low spin. And as we look at these energy differences between these d orbitals, we know what happens when electrons absorb light of certain energies, right? What happens when electrons absorb light that has the right energy? They get excited up into higher energy orbitals, right? So if one of these electrons absorbs the right energy of light, it gets excited up into one of these high energy d orbitals. If one of these electrons absorbs the right energy of light, it gets absorbed, it ends up jumping into one of these higher energy d orbitals. Different wavelengths of light have different energies, right? So we know that different energies of light correspond to different colors of light that are being absorbed. And if you remember from your lab before break, you were looking at copper, you saw that copper made solutions with different colors depending on what you put in there. Now you know why you have different colors, right? Because the different ligands resulted in different splitting energies, which meant you had different colors of light that were being absorbed by those electrons, and you had different colors of light being absorbed. Remember, the color that you see is the color that is not being absorbed, right? So when you look at your book there, you have your color wheel that reminds you of that. And reminds you that basically the color that you observe is the opposite of the color that is absorbed. Okay, so when you have the ability for these electrons to jump into these higher energy levels, you see that you have these different colors depending on exactly what those energies are. For transition metal complexes, these crystal field splitting energies almost always correspond to some kind of wavelength of visible light. And that explains why transition metal complexes and transition metal compounds often have these different colors. The copper things are, blues and greens and purples. When we did the iron with thiocyclone, that's kind of a reddish orangish color. We did an experiment where we had some cobalt, there were some pinks and some blues, and you had different colors depending on different kinds of liquids that were present there. So this is why we see the broad variety of different colors in various transition metal complexes. What's the electron configuration for a zinc ion going to look like? How many electrons are in the D sublevel for a zinc ion? 10, right? You're going to take a zinc ion, you're going to take those 2 electrons away from the 4s sublevel, and you're going to have 3d10. And when you have 3d10, what does that tell you about those d orbitals? They're all going to be full, right? So here's your zinc complex. So all of those d orbitals get filled up if you have a zinc ion, right? Okay. Zinc complexes are typically colorless. Based on what we just said here, why are zinc complexes typically colorless? Can I take one of these electrons and move it up here? There's no room there, right? So if I can't make those jumps, I'm not going to absorb that light into the visible region, and that's why, as you've worked with zinc, you've worked with that once or twice before in lab, you notice that solutions are colorless. And because you don't have the empty space here, these high energy d orbitals where you can excite an electron with visible light and make that move up there. So the color that we see in these transition metals is dependent on there being some kind of open, high energy d orbital that you can move those electrons up into. Okay, questions on that? So remember you had some of them unexpected, and typically we saw those when we were trying to get that D sublevel to be either half filled or completely filled. So if you could move, say, 1 electron so that something was half filled or completely filled, you go ahead and do that. One example that we looked at was copper. You just look at copper metal, it turns out to be 5s1, 3d10. So now if you go to the copper 2 ion, you take away the 4s1 electron, and then if it's copper 2, you also have to take away 1 from the D sublevel, so you have 3d9. So copper has still 1 empty space in one of those high energy orbitals, so that's why you see those bluish colors with the copper there. All right, one other thing that we should mention here, and that is that what I have talked about here applies when you're dealing with something that has an octahedral geometry. If you're dealing with something that is square planar, or something that is tetrahedral, the orbitals are going to behave differently. And let's see if we can rationalize this out a little bit here. So, what's the difference between something square planar and something that's octahedral? You got 2 less ligands, right? I mean, if I think about this as being octahedral, I can basically just take 1 off the top, and I can take 1 off the bottom, and I got something that's square planar, right? Okay, so if I have a different number of ligands that are interacting in different directions, that's going to change the potential interactions here. Okay, so if I go from something octahedral to something square planar, I no longer have ligands up here. And what I do have here in the middle is probably going to be held up a little bit more tightly. And so this orbital in a square planar complex is probably going to be a little bit higher in energy, because what I have left is right here in, I guess you could call it like the XY plane, if you want to label these X, Y, and Z. Now, this orbital in a square planar complex is not going to be quite as high in energy anymore, because I've taken away the ligand that would be interacting up here and down here. So things are getting a little bit more complicated than they were in the octahedral case. Okay? What's going to happen to this orbital when I take the ligands away from top and bottom here? It's going to be a little bit lower in energy, because I don't have these ligands orienting or interacting up here. And the same thing should happen for that one that's pointing and just 90 degrees the other way. But this one that's down here where the ligands are still going to be relatively high energy, because things are getting close there. So in a square planar case, instead of having the 3 low energy and the 2 high energy, you get something that looks like this. And your book doesn't talk about square planar, but I will. You can know this. Okay, so in a square planar complex, there's a more complicated splitting of those d orbitals based on the different kinds of interactions that you have in the different directions. One thing that you should keep in mind is that you should expect a square planar complex to always be a strong field. So in other words, in a square planar complex, you'll always fill up these completely, and then you'll fill up this one, and then you'll fill up this one, and then you'll fill up that one. We can do the same kind of analysis looking at something that is tetrahedral. It gets a little bit more complicated because they're not pointing off in a nice 90-degree direction here. In a tetrahedral case, you have something that's basically the opposite of the octahedral case, where you have 2 relatively low energy orbitals and 3 relatively high energy orbitals. Anytime you have a tetrahedral complex, you should always expect that to be weak field. So you're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Now, with an octahedral complex, sometimes they're weak field, sometimes they're strong field. How do you know what to expect for these in-between cases here? Well, whether it's strong field or weak field is going to depend on a couple of different things. The first thing it's going to depend on is which metal you have in there. And as we're looking at these transition metals, as you look at the ones here in the top row of the transition metals, those may be high spin or low spin depending on circumstances. You see plenty of examples of each type. When you get down here into the second row and the third row, and presumably the fourth row, although those are all really radioactive and kind of hard to study. When you get down to the second row and the third row, you almost always will see a low spin situation when you get down to the second and third row of the transition metals. And we won't spend time trying to explain why that's the case. We'll just kind of accept that there. So you will almost always see low spin complexes if you are dealing with the second and third row of the transition metals. The other factor that you have to take into account then is the ligands that are present. Some ligands are more likely to give you small pairing energies or small splitting energies. Some ligands are more likely to give you large splitting energies. And we can arrange these ligands in terms of what is known as the spectrochemical series. You have a partial spectrochemical series there, right about in the middle of your page there on page 607. The ones over on the left side, the cyano ligand and the nitrito ligand, those will tend to give you strong field complexes. Fluoro and chloro ligands will tend to give you weak field complexes. So you're going to want to familiarize yourself with that spectrochemical series, in particular the ones that are on the ends there, because that may be useful to you in looking at an octahedral complex and predicting what we're dealing with high spin or low spin. Okay? So that gets us through chapter 19. On Wednesday, we'll go back to chapter 15 and we'll look at how the formation of complex ions is an equilibrium process. We'll start talking